Hi, my name is Haslinda. I represent my research group, Air Conditioning Engineering Research, or ASER, and the Thermofluids Department, School of Mechanical Engineering, Faculty of Engineering, University Technology, Malaysia. First of all, I would like to thank the IMAT2021 committee for inviting me as an invited speaker to this prestigious meeting event. Before I proceed, allow me to apologize to the organizer for not delivering this speech in real time due to my other commitment. My presentation title is COVID-19, Its Transport in a Confined Space. What is COVID-19? The COVID-19 is an ongoing global pandemic of coronavirus disease 2019 caused by severe acute respiratory syndrome coronavirus 2. It was first noticed in Wuhan, China in December 2019. The World Health Organization, known as WHO, declared a public health emergency of international concern on 30 January 2020 and a pandemic on 11 March 2020. The disease is the third coronavirus of the 21st century. The latest global update on the COVID-19 cases is over 200 million infections with about 4 million deaths. While for Malaysia's latest update, over 2 million cumulative infection cases with above 28,000 deaths. This data was retrieved from the WHO website on 28 October 2021. Where coronavirus originated? COVID-19 has first speculated originated from bats to animals sold for food at the market in Wuhan, China. Recent studies have confirmed that bats constitute a reservoir for COVID-19 virus. Why is it dangerous to us? The virus spreads on moisture droplets through the air or surfaces, eventually finding its way inside our bodies, typically through the eyes, nose, and mouth. The virus is transmitted through the respiratory tract when people breathe in droplets and tiny airborne particles released from infected people when breathing, talking, coughing, and sneezing. The probability of inhaling these droplets is highest when people are adjacent to the infected one. Infected people are more likely to transmit COVID-19 when they are physically close. The droplet size is between 1 to 10 micrometers in diameter. The larger droplet is between 5 to 10 micrometers, travels a shorter distance between 1 to 2 meters from its source. The illustration shows a comparison in diameter between the COVID-19 virus relative to several viruses and human hair. This figure shows that the COVID-19 virus is the tiniest, yet dangerous. The larger droplet usually settles on the ground due to gravitational effects, especially indoors. The infected person may remain contagious within 20 days and spread the virus even if they do not develop symptoms. On the other hand, the tiny droplets, known as aerosol, less than 5 micrometers in diameter, travel exceeding 2 meters and stay in the air for 3 hours to affect the secondary proprietor without contact with the first host. How dangerous is the virus to us? The coronavirus invades the cells in the back of the infected person's nose, reproducing and spreading downward and infecting healthy cells along the way. COVID-19 harms people's lungs who are caused by the disease. These lung injuries can lead to acute respiratory distress syndrome, in which most people with COVID-19 die. Acute respiratory distress syndrome is a severe lung problem. Fluid builds up in the lungs, causing breathing failure and low oxygen levels in the blood. ARDS is life-threatening because it keeps organs like the brain and kidneys from getting the oxygen they need to work. It can also put a strain on the heart. Based on the animation, the yellow clusters represent lung damage caused by the disease COVID-19. 3 common clusters of symptoms have been recognized. The first one is respiratory symptoms cluster with cough, sputum, shortness of breath, and fever. The second symptom is a musculoskeletal cluster with muscle and joint pain, headache, and fatigue. And the last symptom is digestive symptoms with abdominal pain, vomiting, and diarrhea. Droplets or aerosols are an essential source of contagion in confined spaces. Based on the simulation displayed, without ventilation, aerosols remain suspended in the air, growing in concentration as time goes by. Recent studies reported that the majority of the COVID-19 infections occurred indoors. Many researchers agree that a proper ventilation system is essential to combat the COVID-19 virus inside indoor spaces. The American Society of Heating, Refrigerating, and Air Conditioning Engineers, or ASHRAE, has introduced and adopted a new direction to alleviate the airborne transmission inside buildings. The regulation focuses on increasing the air exchange rate, supplying adequate outdoor fresh air, filtration, and extending ventilation duration. The ventilation system's performance is determined through airflow characteristics and the air exchange rate. What is an air exchange rate? An air exchange rate is the number of times per hour that fresh air from outside enters a room and is mixed and exchanged with stale air from inside. The air exchange rate tells us how fast we can clear the room from any airborne contaminants. What is it this important? Because if the air change rate is too high, a room loses air spent on cooling. If the rate is too low, the room air becomes stale and stagnant, leading to a build-up of toxins, viruses, and pathogens. Based on this illustration, 2 types of airflow enter the house. Fresh air from outside and cold air from the air conditioning specified air vents. The purpose of this airflow is to exchange air with the warm air inside. This process repeats, and the number of the cycle is based on the number of occupants, building location, and type. Understanding the air exchange rate of a building is essential for health. The table shows the air changes per hour and time required for airborne contaminant removal by efficiency. For example, based on the table, it takes 138 minutes to reach 99% efficiency with 2 air changes per hour, but less than half an hour with 10 air changes per hour. The time required to reach 99.9% efficiency is even longer at nearly 3.5 hours with 2 air change removals and 41 minutes with 10. The number of minutes required to achieve both levels of efficiency declines as the number of air changes per hour increases. ASHRAE recommends 3 to 6 air changes per hour for offices and schools to help with the pandemic. The higher rate can be accomplished by opening doors and windows and using filtration systems. However, the trade-off from increasing the air exchange rate decreases energy efficiency. When inside air is mixed with outside air at the proper frequency, air quality increases and the chances for epidemics or other health risks decrease. Not only that, the excellent air exchange rate, utilizing both passive ventilation such as doors and windows and active ventilation such as heating, ventilating and air conditioning systems, helps ensure that everyone inside is as comfortable as possible. There are various methods used to analyze the airflow characteristics and ventilation performance inside a building. The commonly used methods are empirical models, analytical models, zonal models, multi-zone models, small-scale experimental models, full-scale experimental models, and computational fluid dynamics models. However, the most attractive method is computational fluid dynamics modeling, since it is the most reliable to assist in the design and evaluation of the performance of a ventilation system regarding thermal comfort and air quality. For instance, the diagram shows an empirical air exchange model for residential and commercial buildings. The model considers 3 types of airflows across building envelopes, specifically leakage, natural ventilation, and mechanical ventilation. In this figure, a 3D model of an open-plan office building with stack-assisted cross-ventilation is shown. This study uses a multi-zone model technique. The study uses a building dynamic simulation tool, IDA, Indoor Climate and Energy. This tool is used to predict thermal comfort, indoor air quality, and energy needs in buildings. As mentioned earlier, computational fluid dynamics models are the most attractive method since they are the most reliable to support designing and evaluating a ventilation system's performance regarding thermal comfort and air quality. For instance, as shown, the Fluid Dynamics of Disease Transmission Laboratory at MIT conducted a study to visualize potential real-life situations of how COVID can spread among students with just one positive COVID case in the room. An open door and window in the classroom can increase airflow, which helps flush out old air from the room and let fresh air flow in. However, the seating arrangement is also essential. Based on this illustration, cautions not to put kids near where the air is flowing in or where it is flowing out to avoid creating a potential transmission hot zone. In another situation, the findings indicate that schools must not use plastic partitions since they will cause more harm. Initially, the plastic partitions were intended to block larger droplets. However, based on the simulation, it can be seen that the adverse effect creates good airflow to be hindered and allows any trailing viral particles to hang around longer. CFD simulation is an essential tool for designing ventilation systems in critical healthcare facilities. In this model, the researcher is trailing particulates within the room and showing air velocity gradients. The model was developed through specific information based on a typical operating room ASHRAE Standard 170 ventilation of health care facilities. These virus flow simulations predict the distribution of viruses in the air enclosed and open environments. such as hospitals and supermarkets. As for the conclusion, a fundamental approach to lowering the concentrations of indoor air pollutants or contaminants, including any viruses in the air, is to increase ventilation, the amount of outdoor air coming indoors. Controlling the environmental conditions of a confined space may offer a feasible solution to increasing the inactivation rate of the COVID-19 virus.